I might go into a sneezing fit at some point because I have a kind of an allergy. So if that is a case, we'll see what happens. Okay, so we kind of covered the basic technology that we needed for the understanding temperature in the context of these thermal geometry, so to speak. And so now we want to kind of apply these to black holes. Okay, so that's where we are going to start. And yeah, so let's start with quantum field theory in black hole backgrounds. So this is the setting in which we will work. So this is the basic context. Okay, so and the basic premise of something like this is that we are assuming that gravity is non-dynamical. But nonetheless, we are interested in space-times which are solutions to Einstein's equations, but also have horizons. Okay, so we are interested in, we will actually work with solutions of gravity, but under the assumption that there is no gravity in the space-time. Okay, so which means that the backgrounds that we are going to look at, the space-time metrics that we are going to look at, are things like Schwarzschild black holes. But once you are there, you are interested in the small fluctuations around that space-time rather than the whole scale dynamics of the geometry. Okay, so that's the premise. So it's kind of important to make it kind of clean and precise as a limit of where G Newton is going to 0. Okay, so it's important to understand in that sense. So G Newton is going to 0 is the limit, but at the same time, the R horizon, the radius of the horizon is held fixed. Okay, so that's what that means. Okay, so note that that means that horizon is G Newton times m. Right? So this means that the mass of the geometry is going to infinity. Okay, so the mass in some, sense of the black hole is basically going to infinity. So this is an infinite mass limit, but note that because G Newton is going to 0, this horizon radius is still finite. Area is, in some sense at least, So yeah, you can, the physical area will be finite, but because G Newton is going to 0, the entropy will be A by 4G will go to infinity. Okay, so it's a kind of a interesting approximation, but the way you should think about is basically this is the quantity that is held fixed. This is the basic ingredient in many. This will kind of give you some orientation in thinking about it. Okay. So the idea here is that we take the Schwarzschild black hole, then we look at quantum fluctuations around it, and then what happens? This is our question. And the reason why we expect that something interesting may happen here, which is not there in the case of Minkowski, is because there are horizons. Okay, because of the horizons, in Euclidean signature, you will have periodicity in time direction, and so we expect temperature to happen. And what physics do we get out of this, and where do we head? This is the question. Okay, so this is one way to characterize our approximation, and in 3+1 dimensions. So these things I think you should kind of work out a little bit on your own. So you can check that G Newton basically goes as 1 by m Planck square. Okay, m Planck is so if you have, so this is, you might have seen all of this before, but G Newton, H cross and C are the dimension full quantities that, instead of working with mass, length and time in the context of quantum field theory, we work with, these quantum field theory and quantum gravity, we work with these as the fundamental dimension full objects. Okay, so because there are 3 of them, there are also 3 of them. So that's why we can actually make this exchange. So which means that you can work in units. Once you choose, instead of choosing units for m, l and t, like meter, kilogram or second, you can choose these quantities. This is some dimension full quantity, right? So you make some dimension for m, this is basically in standard, if you, from Newton's law, we know that this is Newton meter square per kilogram square or whatever. So you can write it in terms of m, l and t. So this is a dimension full quantity. Okay, and this is also a dimension full quantity. It's action, right? And this is velocity, everything. So we know this dimensional quantities, but what it means is that because these are fundamental constants, these quantities, we have some measured value for them in terms of these m, l and t, which there is no natural unit for m, l and t, right? But there are natural units for these. So that's why we set them to 1 and then say that, okay, we measure everything in terms of those. Okay, so So if you, so the point is that because there is a G and H cross and C, you can invert them into M, L and T. So if you have these three quantities, then you can write down a basic unit of M in terms of these by reversing it, so to speak, and then you will get some expression, and that expression I claim is proportional to 1 by MP square, where I have set H cross and C to 1. Okay, now I'm only carrying around the G dependence, the G Newton dependence. Okay. So, so that's what this is. So, so what is that? Yeah. So this means that my M Planck by this M is going to 0 in this limit, in the semi-classical limit. Okay. So this is sometimes called the semi-classical limit. Okay. Semi-classical. Yeah. Semi-classical limit, but also it's the same limit which is also sometimes called the QFT in the fixed background limit. Okay, so so this is this limit, but that means that my R horizon. So also because 1 by M Planck square is also the same thing as L Planck square, where H cross and C are again 1. Okay, so these two things are the same. So this means that my RH is, you can convince yourself, goes like this, right? I'm just rewriting this in a slightly, this way. So what that means is that there is this huge dimensionless quantity which is multiplying in some sense the fundamental length scale, which is the Planck length. This is a dimensionless huge number. And for instance, for a, for the, let's say, I mean this is very approximate. This is about 10 to the 40 for basically a sun. Okay. So which means that this is an extremely good approximation. This perturbation theory in Gn going to 0 is an extremely good approximation. It's a very small number that we are doing perturbation theory on. So in principle it should work very well. Okay. So but we'll see that there are some basic problems that happen, and this is so this is MP by M, or this quantity is 10 to the minus 40. So like the reason why it is so small is basically because of the fact that gravity is a very weak force. So, sorry, which one? It's more like it's not. See, there is no direct quantization of gravity that works, right? But so there is a quantization of gravity that works that in terms of some dual variables, where it is actually an expansion in what is some 1 over n, where n is some gauge theory's rank. SUN. So there is no direct quantization. If you do perturbation theory in 1 over in G Newton, you are basically, there is all kinds of problems. You don't know how to do it, right? There is a quantization of gravity directly. It has not been done, and there are conceptual reasons why I think it will not work. Okay, because those are not the fundamental variables. So in a sense, I mean, so what that roughly speaking means is that we have to be kind of careful in interpreting these calculations that we do in this limit if we genuinely want to think of these as perturbation theory in around a fixed background. Okay, so if you fully treat, so here Gn going to 0, that's why I said that I'm basically treating my background as fixed, and I'm doing perturbation theory of the fields around it. So there is one slight subtlety to that statement, which is that when I do that, what I'm actually treating as the extra fields in the background, also the metric fluctuations. Okay, so if you have some fixed background, let's say G mu nu 0, then, so this guy is also part of the quantum fields in the geometry. Okay, so this is what I'm holding fixed, and this is my perturbation. Okay, so these guys are quantized, this is fixed, and I'm basically doing it very roughly. You can think it as the leading order calculation in this perturbation theory. So higher than that, it's not very meaningful to do it, because G Newton, when there is gravity, etc., runs in the loops and so on, it's not an interesting thing to do. Okay, because there is we don't know how to do it properly. So G Newton going to 0 is like it's sort of like the classical, the first correction to the classical thing, if you like. That's correct kind of the way to think about it, and that's why we call it semi-classical limit. Okay, so and that's the setting in which we are doing our calculation, and this 10 to the 40 is the reason why this might be a reasonable thing to do. Yeah. Yeah, so the thing that we are really sending to 0 is h bar times Gn. So it's like h bar times Gn. So here I have I'm thinking of setting h bar to 1. So what I'm really sending to 0, that's also one reason why this is a semi-classical approximation. There is actually an h cross sitting there. Okay, so but yeah, so Yeah, so yeah, you can convince yourself that, though you can think of that and you know, you can reinstate the H cross and C's and convince yourself that that's the right thing to do. Okay, so yeah. Okay, so yeah. So and one more thing, for in the physical, you know, our universe, it's an experimental fact that M Planck is 10 to the 19 GeV. Okay, this is one of the few numbers that I remember, and I think it's probably worth remembering. So okay, so yeah, so another thing is that this huge dimensionless number that is sitting there means that if you make dimensional analysis estimates, you can run it. It's not guaranteed that they are correct. It's very important to remember that. You know what I'm saying? So when I talked about the fact that when you compute the curvatures, for instance, and the curvatures are diverging only at the singularity. So I said that, oh, okay, the curvature is becoming large and they become Planck scale or something like that near the singularity. Right? So those statements, they are roughly speaking, you expect them to be true, and that's what people expect. But at the same time, you should keep in mind that you know, the scales at which these things might fail might be corrected by a dimensionless large number. Okay, so that's, you know, for instance, this number. So what we are really saying when we say that, you know, general relativity breaks down at the singularity is that the length scale at which it is breaking down, the R at which it is breaking down near R equal to 0, is basically around L Planck. That's what we are really saying. So that's what it means to say that, you know, curvatures are blowing up and they become Planckian around R equal to 0 at the origin of the black hole. Okay, so but because of this huge factor that is sitting there, we don't really know that that is true. In a full quantum theory, we don't really know that. Okay, it could break down at m by m Planck times LP, which is basically a much bigger number, and that's of the horizon scale. Okay, so the question of whether general relativity breaks down at the singularity of the horizon is something that, you know, from a fully quantum perspective is something that requires thought. Okay, and there are people who disagree on this, and you know, experts have different opinions, but I would say that the consensus, at least for bulk effective field theory, which is what I mean by this, there's another word for this, the modern word for this is bulk effective field theory. Okay, so and this is likely to break down at you know, the consensus that breaks down at the singularity. Okay, that's another reason why these dimensionless numbers are they are hugely important, and we don't really know where they kick in. Yeah, so the opinion is sort of divided about that particular point. Okay. Yeah, so what we'll sort of, you know, one of the ways in which we generally speaking, we'll start our thermal discussion. Okay, so the discussion about black holes and thermal states and so on is, as I said, we can build an analogy between the Rindler and Minkowski connection and Schwarzschild and Kruskal connection. Okay, Schwarzschild, that's essentially the way we will proceed. So I already wrote down the temperature of the black hole previously, but let me just repeat it with all the this thing, all the dimension full quantities reinstated. Okay, so this is the Hawking temperature, and it's extremely tiny. It's for a you know, astrophysical black hole, for instance. Okay, but note that the M is in the denominator, which means that if you can make a black hole which is small, it can be hot. Okay, so roughly speaking, so the point is that, like, you know, one way to remember is that solar mass black hole, roughly it's a few, I think it's, should I say 100 kilometers? It's a few, maybe tens or something kilometers. Okay, so and it's the Schwarzschild radius. So which means, because of this relation, that the Hawking radiation is around a few kilometers in wavelength. Okay, and these are not, like, you know, so that means that, like, for instance, if a Hawking radiation from a black hole, you will not be able to resolve the surface of the sun just like the way we are seeing it when we look at it. Okay, because the radiation is, the size of the object is basically the wavelength of the emitted particle as well. Okay, so there is no, it will just be, yeah, if you could actually take a picture of it. Anyway, so the thing that we want to do is we want to build this connection, Rindler to Minkowski. This is what we really did in great detail in our previous lectures. So we built the, you know, the thermofield double, we talked about the temperature, all of those things we really did in great detail. So this Rindler-Minkowski connection, and there is a sort of a map between that and Schwarzschild And by Schwarzschild, I mean the exterior Schwarzschild and Kruskal. Okay, so this Kruskal extension of this. So this we will essentially be able to directly adapt wholesale pretty much. Okay, so this is what we will do. The one difference is that Kruskal is kind of, you should think of as sort of like an eternal black hole. Okay, the black hole that has been always been present, and you're just taking the Schwarzschild metric and then extending it everywhere. The metric that you're starting with is 1 minus the standard form of Schwarzschild. But as we know, in astrophysical cases, the black holes form by collapse. Okay, and so it is a physical question. If you're really interested in the question of, we will be able to argue that fairly straightforwardly using the things that we already did for Minkowski, that here there is a natural emergent temperature. As you can already imagine, there will be a thermophile double state which will kind of will moonlight for the Minkowski state, and that state will be called so the Minkowski vacuum will be, so the vacuum will be here, it will be called the Hartle-Hawking vacuum. Okay, I'll talk about it towards the end of this lecture. But, so this is the Mink vacuum gets mapped to the Hartle-Hawking state. Okay, so it's essentially if you do a path integral, you will basically, the state that, Euclidean path integral, if you evaluate it t equal to 0, the state that you get is by definition what you call the Hartle-Hawking state. Okay, so we'll talk about it in a bit more. So, and exactly the same way that we found this Minkowski vacuum by doing a path integral in the Euclidean signature. Okay, so what did I want to say? Yes. So yeah, so I wanted to say something but I forgot. But anyway, maybe it'll come back. So okay, so yeah, so the picture that we have in mind in all of these discussions is, so this is our the Rindler Penrose diagram, and this will get mapped to this picture. Okay, and the idea is that we are going to do quantum, if we did quantum field theory here in Rindler, and then we also did path integral to construct a state on this Minkowski line. Similarly, we'll have a state here on this t equal to 0 slice of Kruskal, which will be the analog of the Minkowski vacuum, which is what I call Hartle-Hawking vacuum. Okay, so again, there will be a path integral, and we are going to do quantum field theory on this wedge, which is basically in the exterior Schwarzschild geometry, and that is what will lead us to, similar constructions, essentially completely by analogy. It will, because we have all done all the hard work. Okay, so we can construct all the state and the thermal density matrix and all that. Yeah, so I remember what I wanted to say. So, but this is for the eternal black hole. Okay, for in an astrophysical context, when you form a black hole and when it finally starts evaporating or when it becomes thermal, etc., then you have to. This is a slightly separate question, because the Penrose diagram is not that of an eternal black hole. Okay, so we have to kind of compute this. We have to do it in a slightly different way, and we will. Probably in the next lecture, how to compute the thermal radiation from an astrophysical black hole which formed by collapse as opposed to something that was eternal, and computing its thermal this thing. So the main key point here is that, and this is the calculation that Hawking actually did. In some ways it's a harder calculation, partly because we have done all the hard work already and we can just work by analogy here, but also there is some conceptual issues that one has to deal with. So it's a harder calculation, and that's the first one that Hawking actually did. Okay, so so Hawking's particle creation by black holes, I think it's a difficult paper to read, but it's worth reading because it contains creation by black holes. So so we won't cover it quite the way Hawking does. We'll cover it in a slightly simplified setting. So this is Hawking's famous paper. So, but I encourage you to look at it, even if you don't fully get everything out of it. It will be whatever you get out of it will be interesting. Okay, so yeah. So the one important distinction between here and here is that when I draw it like this, what I mean is really R3,1. Which means, I'm sort of starting with the Rindler, it's the Rindler on this side here, it's Rindler times an R2. Okay, but here on the other hand, you should, in some cases it will be important that what I have is, in the near horizon region, which I can kind of think of it this way. So in the near horizon region where it is basically approximated by Rindler, So this region is here, the geometry is Rindler times an S2 because the sphere is still there. Okay, so this is in the near horizon geometry, this Schwarzschild basically becomes Rindler, but it's important that this S2 is an S2 and not an R2. And the reason why it is important is because in some cases it will be significant that this geometry is not a solution of Einstein's equations. So this solution, this thing, if you demand R mu nu equal to 0, it doesn't solve it. Okay, because there is curvature on the sphere. Doesn't matter how big you assume the mass of the black hole is, as long as you assume that it is S2, this will have curvature on it. Okay, so that will become important sometimes. Here on the other hand, it's a solution of it's flat space, right? So it solves even not just Ricci equal to 0, but Riemann equal to 0 as well. So that's one distinction that can sometimes be important. Okay, so we will exploit that connection and talk about thermal states and all that. But so in order to do that, the first thing we need to solve the Schwarzschild wave equation, the analog of what we did for Rindler, which was solve the wave equation in Rindler space, right? So now what we are going to do is we are going to solve the wave equation, or try to solve the wave equation in the Schwarzschild coordinates. Schwarzschild wave equation. Okay, so this is what we'll make some comments about it. Okay, so that's how we'll start. So the equation in question is here phi is my scalar field. Okay, so the setting is we have Schwarzschild geometry and we have some free scalar field propagating in that background, and we are going to first solve the wave equation, identify the modes, construct the the Hilbert space, etc. Some of these parts we will kind of skip through quite fast because really all the work we need is kind of done in the case of Rindler anyway. Okay, so but the wave equation itself, I think it is worth seeing. So and this is in minus plus 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 signature, and so the general solution we can schematically write as so there are some creation operators, annihilation operators, and then there is some mode plus. I think it would be slightly better to write the F before the A, but okay, let me go with this. Okay, so this is the general expansion, and the point is that this is with this my F has to satisfy. My F is going to be the general mode expression, which is conventionally taken to be of this form. Okay. So this 1 by r is extracted to make the equation a bit simpler. So you will see that the wave equation becomes, it's a little bit simpler, some simplification will happen. So, and these are fixed automatically because of the the invariances, the symmetries of the geometry. So this is the spherical harmonic, just like in flat space. There's no difference. Same thing here. Okay, well, I mean, in polar coordinates, it's the same structure. And so essentially, the non-trivial part is basically that if you plug it into it, the angular part, so you'll have to do separation of variables. That's essentially what we are doing, right? And when you separate variables, the angular part will be solved by this guy, the time part will be solved by this guy, but then there is a radial part, which we'll write down an equation, and we won't be able to solve it because it's a non-trivial equation. Okay, but the fact that it's a solution of that particular differential equation, and it's some differential equation, whether it has a named solution doesn't matter. So that's why, so those are, that's what we want to look at for a bit, because that radial equation contains a lot of physics. Okay, so, so this is my split. Okay, so, so the claim is that now the radial part, so if I demand, so now I plug this into this, then after this replacement, the only non-trivial equation that is left is so this L is the so this is, let me call it R, but so this R star is something I have introduced before, which is called the Tortoise coordinate plus, R plus is my horizon. some arbitrary constant is allowed. Okay, so the point is, I have written my wave equation in terms of this tortoise coordinate so that it takes a Schrodinger form. And that's also one reason why I extracted a 1 by r here. So that will help in the doing of that. Okay, so, and if I do that, so this particular Schrodinger equation is, the Schrodinger type equation is kind of useful because then we can use intuition that is familiar from scattering and etc. in the one-dimensional potential problems in quantum mechanics. Right?
Minus omega square.
There is a minus omega square? You are correct, yeah. So I think it is, it's like this, I think, right?
Yeah.
So, or is it minus plus? No, I think it is this, right? Isn't that correct?
Omega square minus
Omega square minus. Huh?
it was correct earlier. It was correct.
This is, so with this is minus. Yeah, that's right. So if I make any mistakes, I know that you are an absolute specialist on this. So if I make any mistake, just correct me. But it's an important omega square. Okay. So yes. So this is the structure that we get. Okay. This omega square is crucial because otherwise there is no omega dependence on the problem, right? Otherwise there is no wave equation. This guy has no omega. So yes, so but anyway, so the punchline is that it is a Schrodinger equation, and we can, so this effectively becomes our, omega is our eigenvalue, if you like, okay? So, and this VL is actually, we have an explicit form for this VL. So I have written in terms of R star, but I will kind of go back and forth between thinking of VL as a function of R or R star. Okay, so generally speaking, I'll oftentimes write it as a function of R, but for instance, when I plot it, usually I plot it in terms of VL versus R star. Okay, and they are just, there's a one-to-one map between R and R star. So 1 minus R plus by R. So this also, if there is any mistake, you can correct me actually. So this, I think this is correct. Okay, so this is the form of the effective potential. This is sometimes called the effective potential. Okay, so this is, and this is important because this potential, essentially we are solving a quantum mechanics problem, one-dimensional quantum mechanics problem in a given potential. Okay, so the range, so some couple of things to remember, just to, I have said this before, but it's worth repeating, which is that the range of this small r is from the horizon to infinity, while the range of this tortoise coordinate is from minus infinity to infinity, and in fact that's the reason why we introduced tortoise coordinate. We wanted it to cover like a whole real line. Okay, so there is an exam or something, is it today? Is that the reason why there is like a slight decrease in population? I think there is some midterm. Huh? Ah, I see, okay. All right, so yeah, so now let me make some comments about the mass of the scalar field. So one reference, you can look at is Harlow's lectures. There is also an old set of lectures that I gave at I don't remember the number. It's a set of lectures I gave in Croatia long ago, 10, 12 years ago. But I think that my lectures are kind of going to be slightly complementary to it, but I do think that this is sort of there are parts which I'm not emphasizing. You can go look there if you like. Okay. So, but I'm trying to kind of follow Hartle, even though it's not completely following it, but so that you have somewhere to go and look at. Okay. So the statement is that when m is like, how relevant is the mass of the scalar? Okay, is the question. So we will look at two limits where m is much bigger than r plus. Okay, so should probably say that m is much bigger than. Yeah, I think it's correct, right? I think it should be 1 by r plus. Yeah, so if m is much bigger than 1 by r plus, And you can see from this equation that when r is very large, this just becomes a constant, right? So that means that the only modes which actually can be seen at infinity, right? This is like a potential wall, right? And so there is a wall of height m square at infinity. So if your energy is not higher than m square, you're basically not going to see these guys at infinity. And if you're interested in modes, asymptotic modes, then that means that we are not going to care about, we will have to look at omega much greater than r plus. Okay, 1 by r plus or whatever. A little confused. Yeah, I think that's right. Yeah, so this is basically what controls the Hawking temperature. Yeah, so omega will have to be much higher than 1 by r plus. Okay, so and the point is that those scales are not, so we expect that the physics of Hawking temperature, which we know is controlled by r plus, is, if it is omega is much higher than r plus, it's not going to affect our physics. Okay, so that's one reason why this, at least in this regime, we don't care about the mass of the scalar. So we expect that, another way of saying the same thing is that it will kind of be localized very close to the horizon. All the massive particles, there is some kind of a potential well that is dragging it to the near the horizon. And the things that we care about, for instance, the radiation, Hawking radiation, or the statements about temperature that we are making are things about what we measure at infinity. Okay, what the observer measures at infinity. So we don't expect massive particles to play a big role. But I should say that, these questions are always high mass modes, this is the conventional wisdom, I'm sort of repeating it, but one should keep in mind that when mass is high, you are probably dealing with some UV issues and so on and so forth. Whether any of those things are relevant in the full quantum gravity, there may be some subtleties there. Because these things essentially are getting trapped near the horizon. Maybe something may be significant. And, so I'm just, I'm not saying that is the truth, but it may be something to think about. So what we'll do is, because of this reason, we are going to set m equal to 0. Okay? So we are going to be interested in modes which are, roughly speaking, because m equal to 0 modes are the most significant at infinity. That's roughly the reason. Anything higher, it's going to be more and more trapped towards the horizon. Okay, that's roughly the idea. Okay, so we set m square equal to 0, and in terms of this, again, Pradipta may correct me. So far away, this is the form that it takes. So r star going to infinity is the asymptotic region, and r star going to minus infinity is the okay? So these are the two behaviors of this potential, so V of L. So note that it's an L dependent potential and it falls off at infinity, but that's a power law fall off. This is basically the fall off that you will see in flat space as well. Because asymptotically, this is, this tortoise coordinate is really kind of the same thing as R. Okay, so this is a subleading correction. So if you have at large values, this is the standard angular momentum potential drop off that you see for radial equations in flat space. So that's what this is. But this is non-trivial, and this is the property of the black hole. Okay, and this we can confirm it's right or not. So, but for m equal to 0, I claim that this is correct. Okay, so this is, again, you can see that there is, so the important point here is that we can draw a picture of the potential. We call it R star, and this is R star, and this is the horizon. So this is towards the horizon, and this is towards infinity, and the potential basically takes roughly this form, etc. Okay, so this is the structure that it takes as L goes higher. So as L becomes higher, there is a barrier, and this is sometimes called the angular momentum barrier. Okay, so the properties of this wave equation are quite, quite important, and I think that not all of it has still been extracted, possibly. Yeah, so you can see that in this, in this, what is it called? In this tortoise coordinate, the potential basically dies off near the horizon, which is at infinity in this picture, in minus infinity in this picture, and also at here. Here is a power law fall, here is an exponential fall. And you can also try to draw it in R, and I think it basically, if this is the horizon, I think it takes some form like this. Okay? So it basically dies off quite fast, something like that. So you can try to do, but we won't really need it too much. So this is in VL as a function of R, and we won't really need it, so I just drew it so that you can take a look if you like. Okay, so any questions? It's kind of a heuristic argument. You should not take it too seriously. I'm just saying that, so the mass of the scalar, so the point is that the potential at large R is basically bounded by m square, right? If R is very large, this just becomes a constant at infinity. So the modes of the massive scalar that will contribute to the discussion for an observer at infinity are those values of omega which are greater than m. Otherwise, it will not reach infinity because the potential is, instead of seeing this, you will see some kind of a place where it will be finite. Okay, so and the claim would be that any mode that matters to an observer at infinity, it has to have energy greater than that so that he can reach infinity. Right? It's like a potential well. So, and if we cannot reach at infinity, it doesn't matter. And so the rough idea is that if the potential has slight confining properties for finite m. That's all it is. That's basically what you're saying. And it's more like a rationalization for ignoring it. I don't think it is a super serious argument, but I think it is, at least at this level, it is true. Okay, at least at this level, it is true. Yeah. So, and the point is that we are going to worry about massless scalars. They are the ones which we expect are important. Okay, so massless scalars we definitely think are going to be important. Massive things, especially for very high mass, doesn't really matter. That's sort of the message. And I should emphasize that many of these things can actually be repeated even with finite mass. It is not like a serious obstruction to that. But yeah. So let me give you a couple of small exercises. So one of them is that the peak of this potential for any value of L happens at at order R plus. So which means that it is higher than R plus, it's outside the horizon, but it's not way outside the horizon. Okay, it's roughly around 3.5 to 3 R plus. So that's the regime in which it lies. So the peak will always, for any value of L, for any L, okay, R max is equal to order R plus. Okay, so R max means the place where V is max. That's what I mean. So and for L going to infinity, I think it is for L going to infinity, R max is 3/2 R plus. Okay. So these things you can just immediately check, and very roughly, and this is another important fact, so its V max is approximately L square. Okay, the peak is L square, so the higher the angular momentum of a mode, the more securely it is trapped behind this angular momentum barrier. So there have been various ideas, and we are not going to discuss it, at least not right now, is that these modes that are trapped behind the angular momentum barrier are what are responsible for the entropy of the black hole. It has been around for a while, but it has never been completely made into a concrete idea. Okay, so and that's the reason why I kind of thought I'll mention this, because I think that this is kind of an important thing. Okay, so any questions on this? So the point is that if omega L is greater than the barrier height, you can see it at infinity. If omega L is less than this, they are trapped, at least in a manner of speaking. So propagates to infinity. This is a kind of a classical statement. You should understand that, because this is like I'm looking at the potential and looking at the energies of the modes and saying that they can go to infinity. Quantum mechanically, of course, they can tunnel. Okay, so but this is propagates to infinity, etc., etc. Okay, and these two sets of modes together with omega L, which is of the order of 1 by r plus. Okay, omega L of the order of 1 by r plus. So there is a lot of physics in these modes. Okay, so which we will have something to say about in the next lecture. Okay, so so the point is that this potential here, now we can talk about, so what we are interested in a standard quantum mechanical problem is that there will be modes going this way and this way, right? So e to the minus or plus I omega r star on either side of the barrier. So those are the general modes that we have. And from the point of view of the Kruskal picture that we drew, so which is like this. Okay, so note that all of our discussion is happening only in the right wedge. We are not talking about the full black hole space-time, the Kruskal. We're just solving wave equations here, and in principle we can quantize everything here because it's a globally hyperbolic piece. Okay, so this, if you have, if you include this, so this picture is kind of like there is an e to the I omega t. Also, we are adding here. Note that this is like a time-independent Schrodinger equation. Okay, so but if you are also introducing the e to the minus I omega t and plus I omega t and talk about positive energy modes, then you can have natural notions of modes propagating in this way. Okay, so essentially the idea is that time is always going upward. So if you are coming inward from, so these guys are propagating inward from the boundaries. Note that in order to talk about a propagation, I need to introduce a time coordinate Schwarzschild. That's the reason I'm speaking in that language. But here also it is sort of intuitive. Okay, so so there are these incoming modes. There are these modes that are coming from the horizon, and then there are these modes that go into the horizon, and then there are these modes that go outside the horizon. Okay, so the point here is that in order to talk about a certain, if you impose boundary conditions on these class of modes that we have here. So what I mean by, an example of a boundary condition. So let me define what are sometimes called in modes. Okay, so here essentially this psi omega L in is when r star is going to minus infinity. Okay, and I think this is plus infinity, right? Let me write it and then maybe I'll fix it. So this is when r star is going to plus infinity. Let me write it like this, but I'm a little confused now. So these modes are the modes that you get when you have, so what I'm saying here is that, so these, I wanted these to be, so if I wanted these to be these guys, okay, the modes are coming here, going this, and there is nothing here. So this is a choice that I can make, okay, and this is what I wanted to define to be in modes. And so this is a little bit tricky because of the fact that there are, so I think this is actually plus infinity and this is minus infinity. Okay, so is that correct? So what I want is that but I think I can go outside here. No, okay, this is correct, I think. So what I want is, I want to demand that there is only incoming modes on this side, right? So that means, yeah, that's right. So this and this. Is that fine? You understand the logic? So essentially what I'm saying is that on this side, I only have propagation in this direction. So that's what not having any modes here means. Okay? And so essentially what I'm saying is that the in modes correspond to this guy being eliminated, and that's what this is. Okay, and so these two on the other hand, I have two kinds of modes. On this side, whatever can happen on the outside. So I'm saying that these kinds of choice of boundary conditions will be important for us in defining some of the modes when we are talking about Hawking radiance, in the collapsing case, for example. Okay, and the reason, so the idea here is that like if you need to choose some boundary conditions on your the psi omegas that I'm defining in order to fully define a complete set of modes. So it's, whenever you talk about a complete set of modes, you're talking about a complete set of modes with a fixed boundary condition, set of boundary conditions. So, and in this context, this choice of boundary conditions is sometimes called a choice of vacuum. Okay, so the choice of that, the reason why we say that is because ultimately when we elevate these things to modes and their creation annihilation operators as defining the Hilbert space, that will correspond to a particular choice of creation annihilation operators which are multiplying these particular modes. Okay, so they define a Hilbert space and an associated vacuum. So a choice of boundary conditions is sometimes called a choice of vacuum. Okay, so I just want you to see it for the moment. Okay, the boundary condition choices are an important ingredient in the definition of a vacuum. That's what I want you to take away for the moment. So, and we will use these kinds of different boundary conditions when we do the Hawking temperature calculation in the background of the black hole. Okay, in a collapsing geometry. So, any questions here? Here, I'm not really doing anything with them. I'm just introducing the fact that boundary conditions are important.
So these modes are open as single Cauchy slides, or like the time is not explicitly.
So the boundary conditions are basically placed in here. That's where we are placing the boundary conditions. It's not, so yeah, I mean there is, so the question of what kind of radial solutions should we admit in our Fourier expansion is what is being determined here. Okay, so given these, then we can, so right now note that I'm actually not fixed the normalizations here. The normalizations are not important at the moment because this is still a more or less classical discussion. But if I want to fix the normalizations of these things, then you'll have to worry about the kind of things that you're talking about, which is basically about which Cauchy slice am I using these modes and how am I, there is the Klein-Gordon inner product that I talked about, we'll have to use. But right now, I'm just introducing the fact that these boundary conditions are what fix my psi omega L. That's all I'm really saying. Okay, so but for different choices of these boundary conditions, there exist different kinds of these, in, out, up, down, etc. So a good reference on this is a book by Frolov and Novikov, who do it in great detail. So, okay, so we can take a look at that if you like. Okay, we won't need much of it. We'll just need a bit here and there. So I just wanted to introduce the fact that defining a boundary condition, and by boundary condition I mean physically motivated idea of what kind of waves are we going to look at. Okay, and that is basically why I'm going to define some choices of vacua for us eventually, like a little bit more than that, but yeah, so that's what we will have. So any other questions? Okay, so what's the time? Yeah, we have time. Okay, so now, so this is sort of the setup of the, we need these mode functions and some discussion of this in order to talk about what we want to talk about next time. And so that's, we will use these things in order to talk about Hawking radiation in the collapsing black hole background. Okay, but for many formal purposes and many theoretical questions, oftentimes working with the eternal black hole is what is interesting and important. Okay, so Hawking did this slightly harder calculation, and it is important to do it because we want to really establish that even the collapsed black hole can have Hawking radiation at late times. That is important to do that calculation, but at the same time, for many purposes, it's somewhat cleaner, and also for many purposes, it's theoretically more interesting to look at the eternal black hole itself, and that's what I told you about the Hartle-Hawking state. Okay, so there the analogy. So we'll just introduce the Hartle-Hawking state, say a few words about it, and close today's class. So Hartle-Hawking state, we want to work as much by analogy as we had with when we had Minkowski space, with the Minkowski situation. So Minkowski situation, what we had was that we had this, This was our Penrose diagram, right? So what we did, in effect, when we introduced the Minkowski vacuum using path integral, is that we cut the space-time here at the t equal to 0 slice, and then just simply attached a Euclidean slice to it. This is what we did, right? We just basically attached a Euclidean slice to it and integrated it. This is what we did. So, and right. So, and you know, you could think of this in our, if you remember, there was a beta by 2 rotation along this. Maybe it is better to draw it like this. Okay, I'll draw it like this, but you should understand that the lower part is Euclidean signature and the upper part is Lorentzian. So if you remember, this was beta by 2, which was equal to pi in the case of Rindler. Okay, so this thing was, I moved by pi, right? If you remember, there I drew the picture like this. I had a, you know, if the cut was here, I drew this and I said that we are moving by pi. Okay? So exactly the same logic applies here. I just delete the lower part and I attach a Euclidean piece here. Okay, and this I move by the beta Hawking by 2. Okay, so this, so the idea is that I'm doing a path integral on a Euclidean slice on, you know, on half of a circle, if you like. Okay, so, and the point here is that, like, you know, in the Euclidean geometry, so we can draw. So here, for instance, the Euclidean geometry, if you extend it, it was just a plane in written in polar coordinates. Okay, but here note that because of this beta h by 2, it's not a plane. Because it cannot really be, so this beta h by 2 is the periodicity at infinity. That's something to remember. Okay, the periodicity at infinity, and on a plane, the periodicity is everywhere the same. It's pi everywhere. And in fact, it is pi here as well. Okay, but on a black hole, if you remember, the Rindler metric, the Rindler style metric that we had for the near horizon geometry of the black hole was of this form. Okay, d rho square plus rho square by 4 m. I'm setting g equal to 1, etc. So this was my Rindler metric, near horizon metric, right? So, and here the periodicity is not, asymptotically the periodicity is the Hawking beta h, 1 by 8 pi m or whatever. Okay, but note that it cannot be the same everywhere, because if you had it everywhere, near the tip of the cigar, you will end up having a conical defect. Okay, I mean, what I mean by the periodicity is the same, but you cannot think of any pure analogy with this Rindler case, because it is not going to be, it is not a plane. You have to think of it as a cigar. Okay, so you have the periodicity in the asymptotic region is beta h. Okay. So periodic this thing, but here it basically is going to be just flat space because of this curvature factor. So I'm basically compensating for this 4m square by adjusting the periodicity as infinity, so that near the horizon it becomes flat space. So it's basically not an empty or, you know, not just an R2 written in polar coordinates. It's some kind of a warped geometry, which at the tip of this cigar becomes you know, flat space, but asymptotically the periodicity is not 2 pi. Okay, so that's why this is sometimes called a cigar geometry. And the idea, so when I say this, so, you know, here what I did was, you know, when I did this Rindler calculation, I basically did the path integral here. Okay, I thought of it as a you know, polar coordinate flat space, and then I did the integral along pi. Okay, in the lower half plane. Okay, so the analogous thing here would be, okay, so this is, I will cut my cigar like this, and I'm going to do the path integral along this direction. Okay, so here, I mean, you know, it's like, because the conical defect is not there, this is kind of like an extreme, you can think of it as a flattened out version of a cigar, this guy. Right? So if I just open it out, it basically just becomes this, if it did not have any curvature. The curvature matters and it affects the temperature, but if it did not have any curvature, I could just spread it open and it becomes the Euclidean flat space. Right? So here it is not, but the point is, because I'm doing a path integral only on half of my Euclidean space, I'm only doing the path integral. You know, this is the part, the lower part of it is what I'm really attaching here. Is that clear? If I can go through that, if anybody has any questions, and this is kind of an important point. So if the geometry of that picture is not clear, I can repeat. So one thing to remember is that in all these pictures, I am suppressing the S2 that is associated to this geometry. I'm not, here also I'm suppressing the S2, and here also I'm suppressing the S2, here also. Because each point there is an S2 sitting there, and note that the S2, the radius of the S2 is constant. So I can think of it as a S2 multiplying this, sitting on every point on this geometry, but it doesn't do anything, so I can ignore it. So the only thing that matters for this calculation is the periodicity in the time direction, in the Euclidean time direction. So that's why I have cut the path integral here. And my idea is that basically you will do this integral here, the Euclidean path integral, and you get some state. And that state is the state that I should consider as the natural vacuum state of the Kruskal manifold. That's the claim. Okay? Just as Minkowski vacuum is a natural vacuum state here, I should do the exact same path integral and write down a state here, and that state, you remember that we did that path integral and we wrote it as a thermofield double. So that thermofield double state between the left and right wedges is what the Kruskal vacuum should be. Okay, the natural Kruskal vacuum. And that Kruskal vacuum state is what is called the Hartle-Hawking state. So the important point here is that when I was discussing the modes in the exterior Schwarzschild before and the modes here, you should distinguish them. They're not the same. So those guys are more similar to the Rindler calculation that we are talking about. Okay, this is the full Kruskal manifold, and in that sense it's more like Minkowski. Okay, and what we will, and so we can, because of all the homework that we have already done with Rindler, we can just immediately write down the answer for the Hartle-Hawking vacuum, which I will call psi HH. So this is the analog of what I was calling omega for Minkowski. Okay, so this is basically just going to be sum over, this is chalk, so by 2. It's the exact same form except the temperature has changed. That's it. Because see, the note that you may wonder, oh, what if my field I'm doing this path integral on a on a Kruskal space and not in Minkowski space. Oh, should I worry about this I? But these I's don't really contain any information. I have just told you that they are contain the information in the sense I'm dealing with my ignorance of I's anyway, even in Minkowski space. If I'm computing the spectrum of a scalar field, exactly. Let's say, note that I'm not making any assumption that the theory is free. Not making any assumption. This is still a completely, it can be any arbitrary quantum field theory. As long as it's well defined, it will have a spectrum. And those eigenstates of the quantum field theory, anyway, I don't know how to compute them, but as long as I know them, I can use this technology to write them. So this is what is called the Hartle-Hawking state. So, but the first person to write this explicit expression was actually Israel. So it should really be called Hartle-Hawking Israel state at the very least, because in none of the discussions of Hartle and Hawking, you will actually find the Hartle-Hawking state. Okay, so they talk about it's like there is So I mean this particular form of writing, in particular, note that this is a Lorentzian object, but because we have constructed a state, it's living in a Hilbert space. It has a natural. Now you can evolve it if you want. Okay, if you know the Hamiltonians, etc., you can evolve it. So it's important that this state is it's a Lorentzian object, and this object in this particular, what is called the thermofield double form was written down by Israel. And this was written down, it's kind of like, this has been so important for many of the discussions in the last decade in the context of, black holes and information paradox and all that. But this object in the context of black hole, the idea that you can interpret the eternal black hole, the states in the eternal black hole background in terms of a thermofield double was Israel's idea. Okay, and thermofield double itself was a fairly new idea at the time. So this is a pretty bold proposal. Okay, so that's that. Any question there? So let me also say TH is, I've written it many times before, but I'll just write it one more time, is equal to 1 over beta H. Okay, any questions there? Yeah, so this state is defined on the Kruskal manifold. And of course, once we have a thermofield double, you can trace over the left wedge and write down a thermal density matrix for the right wedge, right? Just like we did. So all one has to do is So all one has to do is you can define the Hawking density matrix, which is trace over L of this psi Hartle-Hawking, and just by tracing over this direct calculation, you can show again that this is nothing but e to the minus beta h omega I. Okay, so both are in the right wedge now. Okay, so this is just this is the density matrix clearly. Okay, so so that's what this is. So this is the thermal density matrix. This is the reason why we have been seeing thermal behavior on the right wedge or on the Rindler wedge or on the exterior Schwarzschild geometry. And so from this geometry, it should be clear that if you go from, if you move by beta h by 2, you go from the right wedge to the left wedge. Okay? So Euclidean evolution by beta h by 2 will take you to the other half if you do it, if you interpret it in the Lorentzian theory. And one way to see that is basically that if you remember, I wrote down this Rindler, the formulas connecting Rindler and Rindler and Minkowski, where the Minkowski coordinates were rho times cos tau and the other one was rho times sinh tau. So if you analytically continue, that will basically become the shift by a factor of pi essentially. Okay, and so that will take you from the right wedge to the left wedge. So that's what really happens there. Okay, so this is an important and useful thing again. The fact that if you move by beta h by 2, you go from the left wedge to the right wedge, or vice versa. Was there a question? You had a question? Okay. So I think that's kind of some of the main ingredients that we want to talk about. So I'll just say a couple of words about what we are going to maybe talk about next time, which is kind of related more to not the eternal black hole, but to the collapsing black hole. So the point about the collapsing black hole is that very roughly, so people usually, it's hard to draw an exact Penrose diagram for a collapsing black hole. The reason is that the metric, first of all, for a collapsing geometry with matter, etc., nobody knows really how to write down. So what people usually do is draw a picture like this. Okay, so you have, this is your horizon, and then this region is somehow you pretend that this is matter. Okay, and this is, I think these pictures were first drawn by probably Hawking for the collapsing case. Okay, in the paper that I wrote down before. And so these pictures are what you can use. What you kind of imagine is the Penrose diagram of collapsing geometry is. And then the idea is that you want to compute these, the idea is that let's say that there is no incoming modes in the past. So you impose a boundary condition such that there are no incoming modes from the past. And then, but if you compute what happens in the future, you will find that there are modes coming out this way. Okay, so that's roughly what Hawking showed in his first paper. And so now the way things are interpreted, now we will say that this is basically in what is called the Unruh vacuum. The calculation is being, I'll explain what that is in the next lecture, but so next lecture is somewhat important. So this is what that is. Okay, so that's what we call, so Hawking's original calculation is in what is called the Unruh vacuum, and that's basically a statement only about the exterior part in a collapsing geometry. Okay, and so this is a hard calculation for various reasons. Okay, so and we will not do a completely thorough job. So partly because of the fact that there is, Hawking introduced what is called a geodesic or iconal type approximation to you remember I told you about the Bogoliubov transformation between the different modes, right? So in order to explicitly do the Bogoliubov transformation is hard. Because it is, these are, first of all, I forgot to mention that the wave equation, the radial part of the wave equation that I wrote down for Schwarzschild is sometimes called the Regge-Wheeler equation. Okay, and this equation, as I said, is not generally solvable. So this means that Hawking had to do various approximations. Just the modes are not solvable. That's already a pain, right? It's not like in flat space where the radial modes, at least you know about Bessel functions, they're ugly, but you can do something. But this equation, it's not, you can't write them in terms of well-known elementary functions. Of course, you can start your own radial wave function and call it something, But the thing is, it's not a very well-studied radial function. So it's not a very useful thing. So the point was that what Hawking did was he made approximations to relate between the past, the modes in the past and the modes in the future, which is what basically we call a Mogulibo transformation. And in order to do that, he had to do multiple approximations. And one of those approximations is basically that you can approximate the evolution of the high energy modes which are relevant for this calculation, and one can argue that the high energy modes are what are relevant for this calculation. In that regime, you can treat them as though they were going along a geodesic. Okay, so he makes approximate. That's a remarkable paper actually, because he knew what the answer was. Otherwise, there is no way of doing it. Because he knew what the answer was, so he could find the approximations needed to get to the answer. You know what I'm saying? There is no question about it. I mean, I don't know whether he has said it anywhere, but it seems obvious to me that there is no other way to do this calculation. So anyway, so this is what he did. But what we will do is actually, so that's complicated and messy. You can look at the paper. But there is a slightly simpler setting which in hindsight people have developed, which is to make so this is in some sense a more realistic setting, right? You're starting with matter. So this region is basically what you can think of as like a collapsing star, if you like. Okay, the star is collapsing, and this is the event horizon. So once it goes inside here, nothing can reach here. That's the definition of the event horizon, right? So this was his picture. And that because of the matter and all that, there is a lot of complications, and it's hard to identify a good approximation. But what people do now, or at least there is simpler versions of that calculation which we can do, which is that instead of collapsing a star and matter, which is ugly and difficult to kind of doesn't really matter actually. Like once you know the approximation, you can do them. But it's a slightly cleaner calculation. Instead of sending a matter star made of, let's say, which starts at past time like infinity. So matter is forced to stick to time like geodesics or time like paths. So which means that these guys have to stay here. But if you start in principle with a null shell, right? If you start with a shell with some energy, and you collapse it, you can at least idealize the problem and start the collapse from null infinity. And then you can send this thing in this direction. And the advantage of this is that once the shell has passed through, right? This is basically the trajectory of a shell. So once the shell has passed through, you can use the exact Schwarzschild metric on this upper part. And outside here, it is basically massless and Minkowski. So this is Minkowski space, and this is Schwarzschild, exact Schwarzschild. And you just have to patch them together. Okay? So that simplifies the calculation a lot in some ways. And the place where, this is an instructive picture because it really, it really shows in many ways that, many of the features of the horizon, for instance. Okay? So note that, you started here, but the horizon has already started here. Right? Because even it didn't have to cross anywhere here. The horizon is starting here. So that shows that this is sometimes called the teleological nature of the horizon, which is that it kind of knows about what is going to happen in the future. That's a property of the fact an event horizon, a global event horizon, is a property of the space-time. It's not a property of the local physics here. Okay, so you started it here, and so by the fact that the horizon, so whatever was inside here when this shell started, but of course this is this shell started at past infinity in some sense because it's null time, it's going all the way to the back. But nonetheless, it is interesting that it is not at some particular point where the shell crosses its Schwarzschild radius or something. That's where the horizon is. There is a horizon there, but it also already started a bit earlier in some sense for other observers. Okay, so this is sometimes called the teleological horizon, global horizon. So there are many things which are called horizons, but what I'm really talking about now is what is called a global event horizon. Okay, so and this is the region that is inside, and what we will be interested in is calculating the. We will be interested in calculating this we will not do it in a completely thorough way because I think that it will take too much time, and I want to talk about, more interesting things and more modern things. So, but we will do it, some version of this. Okay? So, any questions?
So the cross sections of this cigar geometry is basically a S2 sphere.
No, this is, just this part is basically S1 times R, right? So this line here, you know, I just cut it off at some point, but it is basically R. So this line is an R, and on each point of that R, there is an S1, right? So, and then on top of it, that sphere will be another S2 if you want. So this is my R, which is the radial coordinate if you like, and then there is a, you know, that radial coordinate of Schwarzschild. Then there is a time which is periodic, and that's this S1, and then there is on top of everything there is an S2 on each point of the cigar. So this is what is the cigar. This S2 is just everything, on each point on the cigar there is an S2. Any other questions? If not, I think